The first talk is going to be given by Dr. Ben Lawrie, who is a senior research scientist at Oak Ridge National Lab, and also the director for the Heterogeneous Quantum Systems Initiative at the laboratory. And he's going to be telling us about practical quantum sensing with squeezed light. So the floor is yours.
Thank you so much. And I guess I'm actually not turned on, am I? Better? Better? Yes. Good. Okay, thank you. And yeah, thank you for the opportunity. Thank you for the introduction. Certainly, as before, please feel free to interrupt with any questions or any concerns as we're going through the talk. And I guess before I jump in, perhaps I should say that the quantum information research and quantum research at ORNL spans much more than what I'm talking about here. I'm mostly focusing on quantum optical sensing for condensed matter applications today, but I'm certainly happy to talk offline about all sorts of other opportunities in quantum information research at the lab. So basic motivation here is that optical probes of matter are ubiquitous. Whether you're talking about biomolecular sensing or whether you're talking about cosmology, understanding light-matter interactions in order to develop new probes of matter is a fundamentally interesting topic. But in many environments, the optical probe can provide seriously unwanted perturbations to the matter that you're trying to probe. So whether you're thinking about optical spectroscopy of biomolecular systems, where your laser readout might fry your living organism, or whether you're thinking about magneto-optical probes in millikelvin environments, where a very small laser power can be sufficient to introduce a substantial photothermal perturbation. These kinds of things introduce serious challenges. And you can think about this, for example, in the context of magneto-optical Kerr effect measurements, where you're just measuring the polarization rotation induced on an optical readout field by some material. So the three data sets you see in this graphic are just three magneto-optical Kerr effect measurements performed with three different laser powers on some kind of conventional GGG bismuth-doped YIG sample. For laser powers varying from 20 microwatts to 200 microwatts. And while increasing the laser power in our measurement substantially improves the signal-to-noise ratio in the measurement, increasing the laser power in the measurement also substantially increases the temperature of the sample that we're testing. So this is kind of a simple but nice illustration of this challenge that we've got when we're trying to execute optical spectroscopies and optical microscopies in cryogenic environments. So we might think about trying to leverage quantum optical resources to improve the sensitivity of these measurements and minimize the optical perturbation induced by these measurements. And the idea of using squeezed light to suppress the noise in an optical measurement is an old idea now. This was proposed by Carlton Caves in 1980. And it's been realized now for quantum enhanced sensing for gravitational waves. But increasingly, we're moving towards integrated quantum light sources where the ideas that have been deployed in things like advanced LIGO can now be deployed in more ubiquitous sensing platforms, whether you're thinking about biomolecular sensing or whether you're thinking about magnetometry or things like magneto-optical Kerr effect measurements. And so that's what I'm going to try to walk through today is how far we have come in squeezed optical readout for quantum sensing applications, and what the challenges are that are preventing further progress at this point. So let's start with kind of state-of-the-art research in magneto-optical Kerr effect measurements. These are all strictly classical measurements. So by Aaron Kapitulnik's group, for example, or Liang Wu's group at Penn, or by Scott Crooker's group at Los Alamos. But in each case, what's happening here is that on the left, a non-zero Kerr rotation in the polarization state of your optical readout field can be used as a quantitative signature of time reversal symmetry breaking in some material that might be induced by unconventional superconductivity, or it might be induced by the onset of some charge density wave. But in each case, there are a growing number of claims and important claims that we can use magnitude optical Kerr effect measurements to probe time reversal symmetry breaking in quantum materials. On the other hand, Scott Crooker's group on the right here has had a very nice history looking at spin noise spectroscopy, where fluctuations in magnetic systems can map onto the RF sideband of some optical readout field. And instead of just reading a fixed Kerr rotation, you might read some Kerr rotation spectrum in the RF sideband, and in doing so, learn more about the dynamics of spin fluctuations in materials. But on the left-hand side, a lot of these phases emerge at cryogenic temperatures. Increasingly, many of these materials, you've got interesting phases emerging at less than 1 Kelvin. So this graphic I showed on the previous slide kind of becomes important here. If we want to be able to resolve nanoradian scale Kerr rotations with absolutely minimum perturbation provided by the measurement, we need to find some alternative to current state-of-the-art approaches like those that these groups have described here. And likewise with Scott Crooker's approach, many of these fluctuating spin systems are emerging at cryogenic temperatures. Ideally, you'd like to be able to look at dynamical properties with a relatively fast measurement, so you don't want to integrate for a long time, you don't want to use a substantial laser power, so what can we do? Alternatively, you might think about all sorts of approaches to atomic force microscopy or scanning probe microscopy. I've highlighted a few different approaches to scanning probe microscopy for resonant enhanced imaging of battery action, for atomic resolution imaging of atoms in liquid, for nanoscale infrared spectroscopies. But in each of these cases, what's happening is that researchers are taking advantage of a strong resonance enhancement provided in scanning probe microscopy by the micromechanical resonance response of your microcantilever. So as a very simple heuristic illustration here, if you look at the displacement of a scanning probe microscope microcantilever and you're measuring it at the mechanical resonant frequency of that microcantilever, then the laser that you bounce off of that microcantilever is going to exhibit a substantial displacement, and you can read out that substantial displacement on some spatially resolving photodetector. If you're working away from some resonance, you're going to see a much smaller displacement, and thus you're going to have a substantially reduced signal-to-noise ratio. So by working on resonance, we get about a 200-fold improvement in measurement sensitivity. But by working on resonance, we constrain ourselves to working at the resonant frequencies where our scanning probe microcantilever works. So if we're interested in probing these kinds of RF sidebands, if we're interested in looking at dynamics in materials at frequencies of hertz to gigahertz, then we need to be able to look at frequencies other than the few fixed resonant frequencies of our AFM probe. Because ultimately, what we see here is that the fundamental noise levels associated with our measurement are going to suppress the things that we're actually interested in looking at. And then the cantilever is going to act as this natural narrowband filter that pulls out signal at only a few discrete frequencies. So working on resonance is great because it gives us an improved signal-to-noise ratio, but it's troubling because it narrows the frequency ranges that we can work at. It slows our measurements because you have to wait for ring down associated with a high quality factor resonator. And it introduces the possibility of nonlinear dynamics that are disruptive to your measurement. So if we can take advantage of a quantum optical readout field to suppress the noise in this measurement, we can move off resonance. And we can start to look at material properties instead of just measuring cantilever properties and then trying to infer material properties from the cantilever. So with sufficient quantum noise reduction, we can enable these kinds of broadband measurements. We can enable much faster measurements, and we can enable fundamentally new approaches to microscopy. Okay, that's the highfalutin language, and now here's why it's hard. So the idea of squeezing is as I said, it's a 40-year-old idea now. And but as a quick background for those who are not familiar, we're starting from a minimum uncertainty state. So we're starting from some system where we have minimized a Heisenberg uncertainty relationship. So for everything I'm going to be talking about today, we're talking about minimizing the Heisenberg uncertainty relationship for the intensity difference and phase sum quadratures of light. And with any classical light source, with a laser, for example, you can minimize the Heisenberg uncertainty relationship. But when you minimize the Heisenberg uncertainty relationship for a coherent light source, you're going to end up with equal uncertainty in both quadratures. And so if you draw some phasor illustrating your coherent light source, when you have minimized the uncertainty in that light source, you're going to have equal uncertainty in both quadratures. And so you can illustrate that as sort of this kind of circular distribution of uncertainty with equal uncertainty in your amplitude difference and phase sum quadratures. On the other hand, a squeezed state of light that takes advantage of quantum correlations in your optical field can suppress the uncertainty in one of those quadratures at the expense of increasing the uncertainty in the other quadrature, thus still satisfying your Heisenberg uncertainty relationship, but allowing you to ideally suppress the uncertainty in the variable that you care about. Now, with two-mode squeezed light sources, we can generate systems where we can measure squeezing in both quadratures, in the intensity difference and phase sum quadratures, by just changing the phase that we're reading out at. And these systems that exhibit squeezing in both quadratures are analogous to the original description of continuous variable entanglement in Einstein, Podolsky, and Rosen's original 1935 paper that described spooky action at a distance. So how do we measure this? You can think, for example, about dual homodyne measurements. So we can take some nonlinear medium. For everything I'm going to talk about today, this is rubidium vapor. So some atomic vapor, or any other nonlinear medium. We can generate some two-mode squeezed light source, where we now have quantum correlations between these the signal and idler field, or this probe and conjugate field coming out of our nonlinear medium. And we can then interfere our probe field with some local oscillator. We can interfere our conjugate field with some local oscillator. And then we can look at the sum and the difference of the outputs of those two homodyne detectors in order to measure squeezing in our phase sum and intensity difference quadratures. Or alternatively, given that we have quantum correlations between photons in these two channels, we can just look at intensity difference squeezing directly on a balanced photodiode. So this, for example, might just be a Thorlabs PDB450 balanced photodetector. And in this way, we lose any information about the phase sum quadrature, but we have a very straightforward manner for measuring our intensity difference squeezing in this system. So this squeezed light source that we're using at ORNL right now, as I said, is based on four-wave mixing in an atomic medium. So we're working near the D1 line in rubidium-85. And we've already heard some very nice talks today about four-wave mixing. So you've got a very similar looking Hamiltonian here. We're converting a pair of pump photons into probe and conjugate photons. And then we're taking advantage of the quantum correlations that emerge between those probe and conjugate photons. And you can go through and in a reasonably straightforward manner, calculate the expectation value for photon number in a system described by this Hamiltonian. And you can then describe the uncertainty in that photon number normalized to your photon shot noise level. And what we see come out of that is this ratio here, where G is the gain of your four-wave mixing process. So stronger nonlinearity yields stronger gain, yields reduced noise relative to your quantum limit. Now, this is an idealized picture. If you include loss in this picture and you say that your composite optical system has total transmission eta, then we end up with this intensity difference noise here that is going to limit towards the photon shot noise level in the limit of infinite loss, but that can limit towards infinite squeezing in the limit of negligible loss and maximal squeezing, maximal gain. So what's actually achievable here? This is an illustration of the four-wave mixing source in one of our labs at ORNL. It takes up a good fraction of an optics table. You've got a decent number of test equipment involved in this thing in order to control phase locking on your homodynamic detection, in order to read out the RF sideband squeezing, etc. But we can measure something like 8 to 10 decibels of quantum noise reduction below the photon shot noise level with this kind of source. And that's reasonably achievable. So we have a set of undergraduate students in the lab this summer working on squeeze quantum sensing with a source like this one, including Malcolm over here. And the expectation is we're going to have a new quantum sensing demonstration by the end of the summer thanks to that work. But there are a lot of challenges here. So 10 decibels of squeezing translates to absolutely no more than 10% loss in the complete measurement from the source to the detector and including everything in the middle that you're measuring. 20 decibels of squeezing would translate to 1% total loss everywhere in the system. So minimizing loss throughout your entire measurement scheme becomes critical because otherwise your quantum advantage is quickly going to deteriorate. And then, of course, just the stability and the complete size, weight, and power requirements associated with this source, as currently demonstrated, is not necessarily ideal for plugging it into an AFM or plugging it into my dilution refrigerator. So what have we done? I like to show this result mostly because this was actually my first undergraduate intern that I had at the lab. So Nils Otterstrom came to us as an undergrad intern, and he had recently heard a talk about nonlinear optical magnetometry, where the precession of atoms in an atomic vapor cell can map onto the polarization state of an optical readout field, and you can use that mapping in order to measure the magnetic field in that vapor cell. And so he was coming to us to work on a quantum sensing experiment already, and he heard this talk about nonlinear optical magnetometry, and he came to us and said, "Hey, is it possible to generate squeezing inside a vapor cell while you're doing optical magnetometry in that vapor cell? Can we read out the field in your cell in situ and demonstrate a quantum advantage in that measurement?" And the answer was kind of. So in a 10-week internship, he was able to demonstrate that compared with a classical measurement, he was able to push down the noise floor by a few decibels. And compared with classical measurements, he was able to enhance the signal on the field by a few decibels. So he got a 5 or 6 decibel improvement in the signal-noise ratio of this measurement compared to an equivalent classical measurement. Now, the kind of caveat that I threw on there is that turns out in a 10-week undergraduate internship, it is not, or it was not in this case, possible to beat the best possible classical state-of-the-art measurement. So he demonstrated that he could improve on an equivalent measurement compared to the way he had set it up. But when he tried to demonstrate a state-of-the-art classical equivalent, he lost most of the squeezing in the measurement and thus lost the quantum advantage. So this then turns into an example of much of the challenge of deploying quantum resources to achieve enhanced sensitivity in sensing modalities that are already used with classical readout fields. So often we can prove that the quantum resource works and measures something, but then when we try to actually improve on the classical readout field, we realize that there's all sorts of loss or background artifacts that contaminate our quantum resources and reduce the benefit of the measurement. So we were able to demonstrate sensing capabilities better than the best possible classical measurement with quantum plasmonic sensors. So the idea here is that localized surface plasmon modes supported, for example, on these nano hole arrays in silver-thin films exhibit strong optical resonances at visible to near infrared frequencies. And we've shown that we can couple these squeezed light sources into these plasmonic media. We can convert our squeezed light source into a squeezed plasmon source, and then we can convert it back into a squeezed photon source again, and we can maintain all of the squeezing that was present in the system minus the loss or the loss-induced change in squeezing that we described on this previous slide. And I guess we've heard allusions to this earlier today as well, right? That your conventional metallic plasmonic media are great platforms for confining electromagnetic fields, for deploying biochemical sensing applications, but in general they're very lossy, and that loss isn't ideal here. So in this case, in this kind of list of publications over here, we were able to demonstrate that we could get to something like 10 to the minus 10 refractive index unit sensitivity, which is fantastic. But it's only a small improvement on the classical limit because we had lost much of the quantum advantage that was present in these systems thanks to the loss in these metallic plasmonic media. All right, so let's jump back to this scanning probe idea. This result over here that was published in Optica was a long delayed result of what I started as a postdoc at ORNL in 2011. And the idea was basically that, hey, if we've got some nonlinear medium, we have our rubidium vapor cell here, and we can generate our two-mode squeezed light source. If we just take one of those two arms, take our probe field, couple it into an AFM, bounce that probe field off of our microcantilever in our AFM, and send it straight to a split photodetector. We take our conjugate field, we send it straight to that same split photodetector. I showed you that kind of very simple animation earlier where your AFM is going to induce some displacement across your split photodetector, and thus you should be able to read out your AFM beam displacement based on the change in relative intensity across your split photodetector. We should be able to take advantage of quantum correlations between our probe and conjugate fields in order to read out the displacement of our AFM cantilever with better than shot noise limited sensitivity. And after 4 years of work, we were able to do so. But the trick here is that with the split photodetector on this printed circuit board here, we were splitting our probe beam in half. And I've told you that there are quantum correlations between the photons in our probe field and the photons in our conjugate field. But for the most part, those quantum correlated photons are distributed across the spatial modes in your probe and the spatial modes in your conjugate. And what we found was that by using a spatial light modulator to manipulate the spatial modes on the probe and conjugate field, probe and pump fields injected into the vapor cell, we could engineer which spatial modes were amplified by the vapor cell, and thus we could engineer the spatial distribution of quantum correlations in these probe and conjugate fields such that the probe photons hitting on the right-hand side of our detector were quantum correlated with the conjugate photons hitting on the left-hand side and vice versa, so that when we did an intensity difference measurement, we maintained all of the quantum correlations in this system, and we were able to get a 4 to 5 decibel enhancement in the sensitivity of this measurement compared to the best possible classical readout. Now, I did tell you a few slides back that we only need to get about 20 decibels to make up for the resonance enhancement, so there's a path there. And I think one of the reasons that there's a path there is that if you squint really hard, this looks kind of like advanced LIGO. We're taking some mirror, in this case an AFM microcantilever, and we're looking at that displacement of that mirror with some squeezed readout field. Now, at that point, from there, it looks nothing like advanced LIGO. But we can read out the displacement of this micromechanical system, and the appeal here is that we can have very low loss systems everywhere in this optics train. So there's no reason that we shouldn't be able to push from this kind of proof of principle level of squeezing here to something much more substantial in order to realize something like the 2 order of magnitude improvement in sensitivity that we need to realize that sort of quantum enhanced scanning probe microscopy that I described earlier. Now, one way we might be able to do that is to move from this kind of approach, where we were engineering the spatial modes in our vapor cell, to a dual homodyne scheme. So what's illustrated here is we take the exact same source, where we have our nonlinear medium generating probe and conjugate fields, but now we generate a pair of local oscillators, and we interfere our probe field with a local oscillator, we interfere our conjugate field with our local oscillator, and we enact that dual homodyne measurement scheme that I described earlier. And the appeal now is, first of all, there is no need to engineer any spatial mode, so we can just focus on optimizing the squeezing and the measurement. And second of all, we can work with a squeezed vacuum state of light and still realize the same quantum noise reduction that we realized with the bright squeezed field over here. So what that means is we can minimize the perturbation to our scanning probe platform. We can start to work at cryogenic temperatures without any laser-induced heating, and we can still realize in this proof of principle here of order 4 to 5 decibels of quantum enhancement in the measurement sensitivity compared to the best possible classical readout scheme. So this worked reasonably nicely. There's a path forward here, but we're still not reaching the sensitivity you could reach by just working on resonance in the first place. All right, now, the thing I would love to be able to show you that I can't show you yet is this idea of squeezed magneto-optical Kerr effect measurements. And so what I've promised the Department of Energy is that I would like to take a squeezed light source, a squeezed vacuum state, couple it into a dilution refrigerator, and read out the Kerr rotation on that squeezed vacuum state with quantum enhanced measurement sensitivity and minimum perturbation to the cryogenic sample under test. And so we've gone through kind of a basic model of this system, relying on the cooling power that we have in our light and cryogenic system in our quantum sensing lab. And we've shown that it is possible to get substantial quantum enhancement in the measurement sensitivity inside a millikelvin environment while operating at close to 10 millikelvin with this kind of readout scheme. So this should allow us to improve on all of these approaches to spin noise spectroscopy and magneto-optical Kerr effect measurements that I described earlier, while absolutely minimizing the perturbation that's otherwise present with macroscopic photon numbers in your laser readout fields. So the first thing we thought we'd try in order to experimentally demonstrate this is just to try to show that we could measure a magnetic circulodichroism response inside a 4 Kelvin Montana Instruments cryostat. And it kind of worked. So with magnetic circulodichroism, instead of measuring a polarization rotation, you're measuring the differential absorption for left circularly polarized light compared to right circularly polarized light. And the upshot here is we said, okay, this is a simpler measurement for us to try because we're just going to do an intensity difference readout. We're going to put a photoelastic modulator in the probe field in order to switch the polarization state of the probe field back and forth between left circularly polarized and right circularly polarized at a frequency of about 50 kilohertz. And then we're going to look at the differential absorption associated with a sample inside our cryostat. And we're going to try to read out that magnetic circulodichroism signal with quantum enhanced sensitivity. And so here is our photon shot noise limit. Here is our readout signal. And with about 5 decibels of quantum noise reduction, we were able to read out this signal. Huge caveat here is there was no sample in the cryostat for that measurement. So the problem we ran into is one that's all too common. As you push down the noise floor in your measurement, this is This is normalized to your photon shot noise level here, but the measurement itself was at about minus 85, minus 90 dBm. As you're pushing down the noise floor in your measurement, you become more and more susceptible to background classical noise sources. In this case, some combination of very small intensity modulations induced by our photoelastic modulator, very small polarization sensitivity to our balanced photodetector, and then some level of RF pickup that we are getting from the RF drive field that was driving the photoelastic modulator. So ultimately, when we put a sample in, we got a much stronger signal. But this was with a relatively bright readout field. We were able to resolve some substantial enhancement, well, some nominal enhancement, let's say, in the readout sensitivity compared with a classical measurement. But this is kind of looking at a reduced noise in the readout field combined with all of these background noise sources that become increasingly difficult to suppress as you try to work at very low noise powers. All right, so that's kind of where we are right now. We'd love to be able to push towards more integrated squeezed readout fields, both for these kinds of measurements and for some of these scanning probe measurements, especially because right now I cannot put this entire optics table with all of these the nonlinear optics onto my dilution refrigerator and easily couple that squeezed light source into a millikelvin environment. And the loss in my current free space optics train in my dilution refrigerator introduces all sorts of challenges to maintaining the squeezing in this system. So to the extent that we can start to engineer our quantum light sources and improve beyond this kind of optics table scale for wave mixing source, that's going to be an important step forward. But the other thing you can think about is moving beyond two-mode measurements. So everything I've described here is really a two-mode entangled state. So these green nodes here just denote your probe and conjugate field. The line in between them denotes the continuous variable entanglement between these two states. But our four-wave mixing source doesn't have to just amplify two Gaussian modes. As I've already alluded to with the AFM effort, it can amplify an image. And if you amplify an image, you're amplifying many spatial modes, each of which exhibit bipartite entanglement between them. And so you can then think about concatenating many different bipartite entangled states into a cluster state. And you can then build that cluster state into a highly multi-mode state that's a useful resource both for quantum sensing and for quantum computation. Now, we heard a little bit about this yesterday in references to photonic quantum computing. The upside with these kinds of photonic cluster states is that they are extremely scalable. So Olivier Pfister at UVA has demonstrated massive scalability in continuous variable cluster states along the frequency comb. Akira Furusawa has demonstrated over 1 million modes along a temporal comb. We've demonstrated some preliminary evidence of these kinds of spatial comb cluster states. So they're extremely scalable. But if you want to demonstrate continuous variable quantum computing with these kinds of resources, you need that non-Gaussian gate. You need that nonlinearity that was mentioned yesterday. And in this case, the most obvious example of such a non-Gaussian gate is a single photon subtraction gate that requires the use of photon number resolving detectors. And suddenly, our nice room temperature quantum photonic platform requires millikelvin detectors. So we've lost some of the benefit there. And I guess the other challenge here is that most of these cluster states have of order a couple or a few decibels of squeezing, and your fault tolerance threshold for one-way quantum computing with these resources is something like 16 decibels. So there's some work to be done in resource preparation. There's work to be done in developing these non-Gaussian gates. But there's a path to transition from the kinds of two-mode quantum sensing efforts that I have described into resources for scalable photonic quantum computation using approaches like this. And some variant of this is what Xanadu is doing, for example. So one of the issues I've run into at ORNL is finding ways to collaborate with researchers across the laboratory. There's 6,000 of us at the lab, and we've got a lot of great people in our QIS section who are focused mostly on quantum optical efforts, developing new quantum optical resources. I sit in our material science and technology division where I've got a lot of great collaborators focused on quantum materials growth and characterization. But I would love to be able to take advantage of many of the resources developed in our QIS section and deploy them for sensing and microscopy in my labs. And so as one small step towards that, I partnered with Munir Alshakan and Joe Lukens over the last few years on their efforts to demonstrate a laboratory scale reconfigurable entangled photon distribution between their laboratories over here in building 5600 and my laboratory over here in building 4100. So this is across a couple kilometers on campus. And they were able to demonstrate that they could reconfigurably distribute entangled light sources across multiple nodes in a fiber optical network using standard telecommunications fiber and using sort of a white rabbit switching protocol. They were able to do so with very high timing resolution. And so now we have this path to deliver both discrete variable and continuous variable quantum optical resources between laboratories on campus, and then ultimately into cryogenic environments for materials characterization. Now, that's a pretty nice step forward, but of course we also now still lose 1.5, 2 decibels of signal just getting from one lab to the other lab, coupling fiber between spaces. So that's a challenge unto itself. So the alternative is to think about starting to introduce integrated photonic systems, which we've also heard about, for generating squeezed light on chip. Now, there has been a lot of great work over the last few years demonstrating a growing level of squeezing that can be achieved with things like thin film lithium niobate in integrated photonic systems. But all too often, those reports describe an inferred squeezing that must be present on the chip. But the squeezing that's actually present and useful for measurement after you actually get light off the chip is another story. And so once again, I think we run into this issue of the composite loss in your measurement between source, sample under test, and detector can really be a challenge to realizing useful levels of squeezing for useful applications. And so we see that once more here with an attempt to demonstrate squeezing in nonlinear fiber. So here, I'm not even going to bother trying to walk you through this setup, but this is a platform for generating single mode squeezing in fiber using intrinsic nonlinearities in the fiber. And in this initial proof of principle, Joe Chapman and his colleagues demonstrated 1.5 decibels of squeezing in the fiber initially. But once they introduced the classical RF over fiber signal that was needed to deliver the local oscillator to the test site over fiber, that degraded the squeezing in the measurement. And then once they delivered it across campus with the RF over fiber effort, the level of squeezing was basically gone, and this is basically gibberish at this point. So once again, that combination of developing new quantum resources, introducing the classical resources needed for the readout, and then deploying them in campus scale networks, a lot of these things are still quite hard. But I think this is a challenge and an opportunity, right? So there's I think now clear evidence that we can improve on the classical state of the art in measurement sensitivity for applications ranging from plasmonic biosensing to magneto-optical Kerr effect measurements and magnetic circular dichroism measurements to scanning probe microscopies. But realizing the level of squeezing and the measurement that we need to really enable fundamentally new measurement modalities, and realizing the scalability and integration that we would like to have in order to deploy these outside of proof of principle demonstrations is still something that requires a lot of work. So I will jump in a different direction quickly and then wrap up. Thank you. So most of my time at the lab has been focused on these quantum optical resources and integrating them into new environments for quantum sensing application spaces. But over the last year plus, we've started developing new approaches for quantum sensing with things like NV centers at ORNL. And given where we are compared to where many in the crowd are, we took the easy way out and bought a commercial system. So we've recently installed a Qunami ambient scanning NV microscope at the Center for Nanophase Material Science. So this is a user facility. It's available to anybody through open user proposals. And we're in the process of installing a low temperature scanning NV system from Qunami this fall. But ultimately, these kinds of first generation quantum sensing platforms, relying on spin defects in diamond, for example, they work. You know, you can now get commercial off-the-shelf systems like this Qunami platform, and you can characterize both DC magnetic ordering in ferromagnetic systems, but you can also look at spin fluctuation. So we've got some temperature-dependent probe of spin fluctuations as you approach a magnetic phase transition in strontium, iron, rhenium oxide up here. And for the most part, all of this is well behaved, and all of this complements these ideas of squeezed magneto-optical probes quite nicely. So our optical probes are limited at best to diffraction limited resolution, and many of them are more mesoscale than that. But to the extent that we can now say, hey, we've got these first generation quantum sensors that work, they're deployable, we can load any given sample, and we can look at nanoscale spin fluctuations, we can look at magnetic ordering, and then we can complement that with more mesoscale optical probes in the form of squeezed magneto-optical readout. There's increasingly that path forward toward using complementary quantum resources to enable a fuller picture of basic excitations in condensed matter. So I will wrap up there and just say that, hey, we've got these resources. They're working now. They're at different scales of proof of principle at this point. But there's a lot of work still to be done here. And I think a lot of opportunities to really start leveraging these kinds of quantum resources as useful platforms for condensed matter physics. And certainly then I should wrap up by thanking my team on our BES project, by thanking the undergraduate students who have worked on this over the past several years, and the students who will be working on it in the months to come. The members of the Quantum Science Center who have worked on this, and John and Joe who worked on the integrated photonic and fiber-based efforts. And this work has all been funded by the Department of Energy through Basic Energy Sciences, the Quantum Science Center, and through ORNL's Nano Center. And I should thank you again as well.
Thank you very much. So we have some time for a few questions.
Excellent talk. I see you have shown quite a few numbers, like 90.
I can hear you okay anyway.
Yeah. I mean, maybe it's 90 dB or sometimes 5 dBs. So what is the theoretical limit of the squeezing?
Yeah.
The practical limit.
Well, DARPA Inspired is demanding 16 decibels out of their new program, completely on chip. 15 decibels has been demonstrated. Ultimately, though, it's a trade-off between loss and gain, and so it's hard to put a fundamental limit on it. But by the time you measure it, you're of course worried about the loss in your detector. You're worried about the loss in your nonlinear medium, et cetera. So I guess, like I said earlier, 20 decibels of squeezing translates to 1% total loss everywhere. Getting much beyond that is awfully challenging.
Thank you for your presentation. My question has two parts. The first part was it's regarding the transducer that you use to take your optical signal into RF and electrical RF signal. Wait, did you actually experience any noise from your detector going from optical to RF? Since there's a lot of challenges in actually taking an optical signal and change that into an RF frequency. Can you elaborate on
Sure.
some of the?
Yes and no. On the one hand, we are, for the most part, using commercial off-the-shelf detectors here. These are Thorlab's PDB 450 balanced photodetectors that we're using both for the homodyne measurements and for the intensity difference measurements that we've modified by replacing the photodiodes with Hamamatsu photodiodes with improved quantum efficiency, but it's otherwise off-the-shelf electronics. Now, I think there's a couple of reasons why we're a little less susceptible to this. With bright squeeze states, we're working with, let's say, 10 microwatts to 10 milliwatts of optical power. That pushes your shot noise limit up high enough that your fundamental quantum limits are then end up above most of the electronics noise available in commercial off-the-shelf detectors. And then likewise, in homodyne measurements, you can put enough power in your local oscillator that even if you're working with a squeezed vacuum state, your shot noises can be defined by your local oscillator at the detector, and thus your electronics noise from a few hertz to a few megahertz can quite easily be handled without worrying about too much electronics noise.
Now, the other part of the question, when you're referring with RF over fiber, you're using the light wave as your carrier. Is that what
that's right? And then you just lock a local oscillator to that.
Okay.
Yes.
Okay. Thank you.
All right, so the next talk in this session on quantum sensing is going to be given by Professor Ashok Ajoy from the UC Berkeley.
Okay, well, it's great to be back here. Actually, I did my PhD across the road at MIT some years ago, and then I was here for a long time attending seminars in this very room. Now I'm a professor at Berkeley and in the chemistry department, and our focus is actually to take quantum science to the real world, and so actually apply quantum mechanical principles to do something useful in real everyday environments. And so while we do work with the cryostats and vacuum chambers, etc., today what I'm going to talk to you about is really applying things to what you would call wet and dirty environments, so cells, structures, various things of the sort. And in particular, I'm going to talk to you about quantum sensors that are deployable. And in my opinion, quantum sensors are very much clear and present. They're already sort of here. And there are applications where one could argue that they could play a real impact in the next few years. So I'm going to tell you about that. So also in the spirit of this talk, I made it very accessible to students, and I would encourage you to ask any questions. But also I'm only going to talk about unpublished work. So no published work. So that is something fresh and new and interesting. So that's Berkeley, by the way. So I'm going to. Go Bears, exactly. Okay, great. So what I'm going to do, the rough plan for today is I'm going to first give you a little bit of an overview about spin-based quantum sensors. So Ben mentioned NV centers, so I'm going to give you some overview about NV centers. But I want to emphasize towards the end that NV centers are only one material in a large class of materials where this is possible. And I'm going to tell you about other materials where this is possible. And I'm going to focus on what we call deployable sensors. So how do you actually take these quantum sensors and put them into or onto materials and then actually detect something useful with them? So I'm going to tell you about that. And then I thought as a new, fresh concept, today I'm going to focus most of my attention on these flow-based quantum sensors based on microfluidics. And Bob is here, but several other people in Harvard were really instrumental in launching this micro droplet technology. I'm going to tell you how we can marry quantum sensors with this technology. Okay, so first, why should one care about quantum sensing? So I'll give you my opinion on it. So I'm editorializing, if you like. But what quantum sensors are really good at, or what quantum things are really good at, is they see the environment very easily. And large part of many people's effort is to try to protect the quantum system from the environment. But in sensing, we actually like this, because that fragility of the quantum system to its environment can be used as a feature in order to detect things that's in the environment. So if you have single spins, for example, these spins are very sensitive to magnetic fields, and so they become very sensitive magnetic field detectors. And so, we're really exploiting the fragility of quantum systems, and ideally, what we'd like to do is to do things that are difficult or impossible to do with current classical technology. And I think that's still an open question, and we'll talk a little bit about it towards the end. But one can imagine building quantum sensors out of various platforms. Almost any qubit could be used as a sensor. But because we are interested in practical applications, instead of using Rydberg atoms, which may need to be in a vacuum chamber, for example, or superconducting qubits, which are at very low temperatures, we're going to ask to do quantum sensing closer to room temperature or at room temperature in materials that are very easily accessible. As any other sensor, what you want is sensitivity, speed, throughput, form factor, etc. Very easy to imagine how you would define a good sensor. As I was saying, spins are very good sensors of magnetic fields. And I think this whole field of quantum sensing, in a way, was launched by the excellent properties of this defect in diamond, which I'm going to give you some introduction to, because it works really at room temperature and is very coherent. But as I'll tell you towards the end, there's actually a wide class of materials where this is possible. Okay, so first, just as a brief introduction to people and students who might not have seen this before, how would you make what is a spin-based quantum sensor? How does it work? Actually, before that, I'm going to tell you about some applications of quantum sensors broadly, and then we'll go on to describing how these spin sensors work. So what could be some applications of quantum sensors? And today I'm going to focus a little bit more on chemistry-like applications, but there are imaginable physics applications as well. So some applications which we are very interested in is spin sensing and polarization in porous materials like metal organic frameworks. So you can imagine, these metal organic frameworks you might have heard about are metal atoms connected to organic linkers that self-assemble into very large porous structures that are highly tunable, and one can imagine bringing guest molecules inside this. This is widely used in the context of carbon sequestration, for example. And this is a very interesting modality to be able to both sense as well as spin polarize other materials. And we'll talk a little bit about that towards the end. An example that has gained a lot of traction a few years ago was trying to do NMR and EPR, or discerning structural information from single molecules using these quantum sensors. So to use a quantum sensor, put a single molecule above it, maybe say how the molecule is folded. But really at the single molecule level, and one could argue that this is sort of impossible with other technologies under physiological conditions. Ben mentioned this, but this has already been commercialized. This is like a scanning tip, an AFM tip, which has got a little spin center at its tip there, and you can scan over materials, very widely used in the context of condensed matter physics, and you can study different materials, spin textures, etc. So scanning of 2D materials, and this is already commercialized. I'm going to tell you about this today. So really using these quantum sensors as equivalent of fluorophores with some additional excellent properties, and trying to do things like assays and COVID tests and things like that, which you can make with these sensors. Applications in biophysics and living cells. So you can actually put these quantum sensors inside cells, inside animals, and study something inside it. So we'll talk a little bit about that. And lastly, studying chemical reactions on surfaces. So trying to do NMR spectroscopy on surfaces and interfaces, that's usually very difficult to do, and then say something about how reactions proceed on surfaces. So, this is a big palette of chemical-focused or nanoscale-focused applications of quantum sensors, but it's wider. You can imagine applications such as gyroscopes and magnetometers and detecting things related to earthquakes and so forth. So it's a really wide field with several applications. Okay, so I'll go back to just giving you some overview about quantum sensors generally. This is a very nice picture of a scanning tip with an NV center and its tip there. So what is this diamond vacancy center? So you take a diamond lattice, and it's basically pure carbon, and you would replace one of the carbon atoms with nitrogen, and you've got a vacancy in the neighboring site. So together then you've got nitrogen in vacancy. There's a lone pair of electron on the nitrogen that's delocalized between these two sites. And this electron is what's used for sensing. It's very easy to make these materials, as I'll describe in a moment. Especially if you make it in particulate form, it's really cheap. So the two properties of this electron that make it very attractive for sensing are, it can be optically polarized, which means that you shine light and you can initialize the spin 100% with light, and you can actually read it out with light as well. And so these two properties are summarized in this chart here. And I'm not going to go into the details of the photophysics of how this works, but suffice to say that under some mechanism related to the excited state, if you shine light, if you've got these two levels of the electronic spin, you shine light and all the population goes into one state, so that's fully polarized. And if you shine light, you're often shining green light and the spin is fluorescing in the red, and it turns out that this fluorescence is state dependent. So you can tell which population level you started with, if you like, by just reading out the fluorescence counts. And so you can read out the spin state with light. And you can do this both at a single spin level as well as an ensemble of spins, so both are possible. So these are what these diamond materials look like. So these are, in this case, microparticles of diamond. This is with a picture with my iPhone camera. But you can see they're very pretty. They're purple in color because they're doped with these NV centers. These surfaces of diamond are actually very easy to coat with various things. So there's actually a company that sells like 100 coatings of things, including antibodies and so forth. They're diamonds, so they're very resilient. I mean, their diamonds are forever after all, right? And very high, you can possibly get very high surface area. The smallest particles we use are of the order of 10 nanometers. Simple to coat, they're biocompatible because after all, they're carbon, they don't react very well with things. And they're low cost. So whenever I go to people and say, oh, you're going to use diamond, this must be very expensive. Actually, not in the case of these particles. So a gram is about $1,000 or so. And they fluoresce very well, and this fluorescence is non-bleaching. So you can get a very strong, stable counts from these particles. Right, so the basic idea of a lot of these sensing tools is this experiment called optically detected magnetic resonance. And again, this is as means of introduction. If you've not seen this before, basically it turns out that the spin state is a triplet. So it's got 3 levels here, but at 0 magnetic field, these 2 levels are degenerate. And that's the transition. This transition is very close to a microwave oven, right? So it's a 2.87 gigahertz. This is on the microwave. And so what you can do is, if you shine light, you get population all in this state. And if you were to bring a microwave field resonant with this transition, then you transfer some of the population from this lower level to this higher level. And if you were to simply look at the photons coming out, you would see a dip or a slight reduction in the number of photons as you hit this transition. And that's because, as I said, the spin of the fluorescence rate is spin dependent, and so it turns out that this level is slightly darker than this, and so you get this transition. So this allows you to basically read out what would be equivalent of an electron spin resonance, or EPR signal of these electronic spins, but now you're doing it with light. And that's very sensitive, so you can go down to a single particle or single spin level. So now you can actually use this as a sensor. Now, how would you use it as a sensor? So it depends on what you're trying to sense. So it turns out that, for example, one thing that people like to sense are paramagnetic ions. And it turns out that sensing paramagnetic ions is very important in many practical applications, including in biology. But it turns out if you have now paramagnetic ions surrounding this NV center, then it reduces what's called the T1, or the lifetime of the spin. And that would change this contrast that you see here in a linear fashion. So if you can measure the change in this optical contrast that you get here, then you can basically measure T1, very similar to how an MRI contrast agent works when you take an MRI scan, except this is an MRI contrast agent, something like at the nanoscale. And you can measure the presence of these paramagnetic ions. And I'll come back to why this may be important in the context of biology later. So this is an example of things you can sense. You can also sense temperature and pressure, because it turns out that if you deform the lattice or you heat the lattice, this peak moves left or right because the zero field splitting is temperature dependent. And so you can get a very sensitive nanoscale measurement of temperature just by looking at the light coming out. You can also detect magnetic fields, so in a similar manner, but we won't talk about that today. So here's another overview slide for students to give you an idea of what are the kind of things people have been thinking of. This is a review paper from Ron Walsworth's group, but it talks about practical applications of quantum sensing with a focus on diamond. So as I mentioned before, detecting molecular conformation changes at a single molecule level, measuring temperature in single cells, quite interesting. In vivo magnetic field activity in animals, so you can possibly put nanodiamonds inside living things and detect firing of neurons, etc. But I think the most interesting application is what's called magnetoencephalography, or MEG, where you're looking at essentially brain waves and trying to reconstruct neuronal activity. Applications towards more electric field sensing, etc. So, these are, I think, one thing that distinguishes these kind of sensing is that it's really eschews a clean environment. So we're not in a vacuum chamber, we're not in a cryostat. We're really trying to go inside things that are, by definition, sort of dirty. And so we're trying to sense in these dirty environments. And a lot of the tricks are in trying to remove other sources of noise except the kind of thing that you're trying to detect. And we'll talk more about that today. Okay, so now I want to focus your attention on some applications that personally I think are very interesting. One is this paper that I'm going to introduce, not for our group, but a group in England, where they did an equivalent of a COVID test with nanodiamonds. So just to give you an idea, all of you are familiar with COVID tests. How they work are these strips basically contain gold nanoparticles that are functionalized with antibodies. And you've got a mobile phase and a stationary phase, and these gold nanoparticles move in a particular way, and the strip that you see is basically the gold nanoparticles lining up in a particular place spatially, and that's what gives you a positive result. Very widely used, and this is an example of an assay, and this is the cheapest, lowest cost assay. You can imagine more expensive assays with sequencing and flow cytometry, etc., but this is the lowest cost assay. So anyway, there was this paper published from a few years ago, where essentially what was done was the gold nanoparticles were replaced with nanodiamond. And quite remarkably, what was gained is a 4 orders of magnitude improvement in sensitivity. So how does this work? So essentially, what they were able to get down to is a sensitivity level or limit of detection level at 800 zeptomolar. Okay, which is rather remarkable. And how this works is basically using the fact that these nanodiamonds, because they have these NV centers, if you apply a magnetic field or if you apply microwaves, as we just described, you can actually modulate the fluorescence at a fixed rate. So gold nanoparticles, when you go down to very, very small levels, so you got down, let's say, a single particle, you have a large amount of background signals that come from various things into your detector. But with these nanodiamonds, you can actually apply microwave fields, modulate that fluorescence, and because you can modulate the fluorescence, you can suppress every other source of background to a very good approximation. So essentially a lock-in detection. And just by this concept of doing lock-in detection, they were able to boost the sensitivity down to 4 orders of magnitude. So this is, I think, a really good example of quantum sensing applied to the real world. Now, you could argue that unlike a $1 COVID test, now you need a laser and a microwave source, et cetera, so it's not very cost effective. But it shows a pathway where you're actually using a spin property, and you're using this microwave transition in the spin, and you're going to use it for something useful. And we're going to, in this talk, we're going to expand on this idea to different types of assays that where the cost is not such an important thing, but you really care about sensitivity and speed of operation. So some of the things that you can imagine doing are, for example, detecting reactive oxygen, which is a very important thing in living things. Okay, so before I get there, I'm going to first tell you about the deployability of these quantum sensors. The takeaway message that I want to leave you with is quantum sensors are deployable to several locations of interest, and one could imagine various ways by which you can deploy them. So first we started doing 3D printing of diamond particles. So, the diamond is a very inert material. These particles, as I told you, don't cost much. So you can literally admix it with your resin and 3D print structures. And it turns out that the structures that come out are full of diamond. So that's a diamond boat. That's a diamond porous structure with walls full of diamond particles. And so you can imagine, so these are not like nanoscale structures, they're still micron scale structures, but you can essentially incorporate the diamond particles with all these nice properties now that you can optically integrate them and do sensing, et cetera, but into structures of interest. Here's another example. This is another type of manufacturing technique called bubble printing. But what's done is you use a gold substrate and use a high-power laser that's focused on these gold nano islands, and then you've got nanodiamonds around, and then every time the laser is focused on the substrate, you get a bubble, and the nanodiamonds are sucked into that bubble, and essentially they get incorporated by van der Waals interaction. And so you can like pattern things. So we patterned Berkeley, and then this famous picture. And the cool thing here is that because of this compactification with the laser, you actually get a very high density of diamond packing on this surface.
What's the size distribution of the diamond?
Oh, yeah, good question. So in this case, the mean size is about 100 nanometers, and the variation is about 20 nanometers. Mm-hmm. So things like this are very easy to do, and so you can imagine making large-scale structures that are now functional in some way, because each diamond particle now can be used for something. Well, this thing doesn't show very well, but this is our second iteration on 3D printing. But here we've made a structure that's called a gyroid, and gyroid is a provably structure with the highest surface area. So there are all kinds of pores in it. This is an SEM picture, and if the light wasn't there, you would see little dots there, and these are all the nanodiamonds that are incorporated into the structure. So in order to see this better, you can actually do a confocal image. So that's what this is. So this is data of slice-by-slice imaging of the structure. So the resin is autofluorescent in the green. So you see all the green stuff is all the resin. But if you were to go inside, you would see red fluorescence from the nanodiamonds. And the way this 3D printing technique works is called two-photon polymerization. And essentially, the nanodiamonds get embedded into the structure, but not very deep. So they are just lining the structure everywhere. And because the structure has these internal pores, each of these pores gets lined with these diamond particles. So this is kind of exciting because you would have this high surface area material, which you can flow things through. And each of these pores that interact with what you flow through is then now a sensor that you can use for sensing. So, this is in full 3 dimensions, and you can make pretty large area devices if you wanted to. So it just shows like things that you can do with deployable sensors. So here's another example of things we've been working with funded by the DOE. So this is diamonds incorporated into roots. So it turns out that, So I went to a conference once, there were 500 people only interested in roots, and I learned a lot from them. But it turns out that there are many interesting problems in nutrient uptake in root channels, the so-called rhizosphere, which is around a root. And so what we did here is to just feed a root diamond particles. And well, if the particles are small enough, the pores of the root are large enough, the root would incorporate the particles into it. So that's what happened here. So this is a root hair, and it turns out the root hair is so small that it's actually optically transparent. So you can actually go and image inside the root hair, and you see the nanodiamond particles undergoing Brownian motion inside the root hair. So why is this interesting? So it turns out some of the questions that we'd like to answer are really nutrient uptake in root channels. When you have a forest fire, basically there's a hypothesis that there's a large amount of pyrolyzed material, which is actually free radical, like paramagnetic species that are incorporated into the soil, and asking long-term questions about how aging is affected by the impact of paramagnetic things in the soil is of wide interest. And I think the more practical thing that you see in the news every day is in the incorporation of microplastics. So you can imagine that these particles are like proxies for microplastics, but you can just image them very well because they're very bright. You can do this lock-in imaging if you want to with microwaves, etc. So you can actually see individual particle as it gets incorporated into the root and finally into the leaf tissue. And so there are some interesting questions related to microplastics as you might see in the news every day. So it's a very timely question. So anyway, this is like some palette of ideas of how you can deploy these particles. So now in the main focus of the talk today, I'm going to tell you about how you can actually incorporate them into microfluidic devices and then use them for something practically useful. The goal is to make these microfluidic assays now with nanodiamonds. And let me just start off by saying that the basic technology you're going to leverage are these micro droplets. So a lot of this technology actually started at Harvard. Bob and David White's, etc. But what it is water droplet in oil. It's an emulsion. You can also do water droplet in air, but what I'm going to show you today is water droplet in oil. And the diamond particles are naturally hydrophilic. So you don't have to do anything. You just like put them into the water and they would go into the water. And I'm just going to go over here and you can see these flowing droplets. And inside these droplets are the nanodiamond particles. So this is a microscope movie and you can see that the particles are undergoing Brownian motion within the droplets. But inside the same droplet are incorporated yeast cells. Okay, so you can, the droplet, what I like about them is that they are like picoliter volume, confined volumes, and you can put stuff inside them. So it's very widely used for single cell analysis and things like that. But you can put single cells, but now you can also put these quantum sensors inside them. So here's some more detail of how this works. I'm just going to walk you through the diagram here. So this is a microfluidic chip. It's fairly easy to fabricate. It's made out of PDMS. This is what one of these channels look like. It's basically got two junctions, which I'll describe in a moment, but you pinch water with oil and then you create these droplets as they look here. And then what we're going to do is we're going to bring them into an analysis region where we're going to illuminate them with light and microwaves. Okay, so we're actually going to put nanodiamonds inside the droplets and then kind of look at them with light and microwaves as they pass through in continuous flow. And then if you want, you can collect these droplets in a collection chamber. Anyway, so I was new to this field and I started working with droplets and I was really amazed by the amazing monodispersity and the sort of regularity of these droplets. So this is how it works. Let me just go back in this movie. Sorry, water is pinched in this channel here. It's a little orifice that it's pinched through, and oil comes from the vertical channels here. And because these two liquids are immiscible, you add a little bit of surfactant, and you get these really, in this case, spherical-looking droplets, but they are very monodispersed, means they are almost exactly the same size. And if you do things just right, you can actually flow them at exactly the same frequency of the rate with a very high precision over hundreds of thousands of droplets. Now inside these droplets, you can pack nanodiamonds, as I'll show you in a moment. So this is like very nice. It's a movable quantum sensor, if you like. So here we are changing so you can control everything in the channel. So I'm sorry, it's too fast, so I'm going to go back a bit. So you can control the spacing between the droplets very easily by microfluidic techniques. And what that does is you would have a second, it's going to come in a moment, you could have a second junction where you push oil through and you can change the gap between the droplets. And you can have all these little confined picoliter volume things that are moving around in whatever shape you want, and you can collect them in droplet chambers. Okay. So here's an example of how that works. So you can make these droplets, you can control the spacing, and then you can do anything you want with them, really versatile. And Bob pioneered this technique of sorting droplets through electrophoresis methods. We're not doing it here, but it's easily conceivable to do. So here's an example now of a fluorescent image. So we actually packed them with nanodiamonds. So the same thing happens, but now they are full of nanodiamonds and you can see them moving around. Well, the picture is not great, but this is a collection chamber, so you can collect a whole test tube of these droplets if you wanted. So here are some more pictures of these nanodiamond particles inside droplets. So it turns out that you don't have to work very hard. You don't even need to coat them with anything. They just you exploit the native hydrophilicity of these particles. So here are different sizes of particles incorporated into these droplets. So 40 nanometers, really tiny. We can go down to 20 nanometers or 10 nanometers. 100 nanometers, a little bigger, and 3 microns are really big single particles. Here is a single particle in a droplet. So because the fluorescence is so bright from these particles, you can actually watch a single particle. In this case, my students made about 20 particles, and you can track in real time their Brownian motion. It actually turns out it's very interesting that the motion is not really Brownian. It's more like what's called a Levy distribution, so it's got a long tail. This is a 100 nanometer particle in 30 seconds of traversal, and a 100 nanometer particle traverses like 10 microns or so multiple times the diameter of the particle in a very short period. And this is an astatic droplet. So if you move the droplet now, especially if you go through a bend, etc., these things are mixing around really well. And so they're very good for detecting things inside because you create this big churn, and anything inside the droplet can possibly come in contact or in proximity with the sensor and therefore can be detected. So as I already told you, what you can easily do is to co-encapsulate with the droplet like single cells, as shown here. These are yeast cells from a bioreactor. And then you can also put nanodiamonds in the same droplet. Right, so now I'm going to tell you about how you can do sensing now, exploiting all these advantages of the droplets deployed in the droplet, the diamonds deployed in the droplet, and flow. So now to give you some, just to go back a bit, we're going to exploit this very basic thing of ODMR that I described previously. So this is the signal from a single droplet. So you've got these nanodiamond particles in the droplet. What you're going to do is move the microwave frequency, and you see this characteristic dip around 2.87 gigahertz, except it's like really noisy. It's a kind of useless, right? It's a very poor signal to noise. You can argue that's because, well, you have a single droplet, not too many particles, the particles also undergoing motion, etc. So anyway, a simple way to increase the signal to noise is to do a lock-in measurement where you can actually modulate the microwaves. So you modulate the microwaves at a fixed rate, and you demodulate the same rate, and a lot of this noise is coming because of background fluorescence can be suppressed, and you can get a better signal to noise out here. But what we want to do is actually to make a chemical sensor within the droplet. And what I'm going to show you, we're going to detect paramagnetic ions. And it turns out that this microwave lock-in measurement is not good for that, because the baseline, so I told you the information is encoded in this contrast value, but this contrast value is susceptible to the baseline drifting or fluctuations in the baseline. So if you were to just look at what this contrast value is as a function of time, let's say over a minute or so, you find that, well, it's a mean value of about 2% or so, but it's fluctuating at about 13% around this 2%. Okay, so, and so if you imagine now you've got some kind of paramagnetic thing that you want to detect inside the droplet, could be reactive oxygen, for example, that's going to change this contrast level, but how well you can measure it, similar to how you would think of in precision measurement, how well you can measure it depends upon the standard deviation of this distribution here. And so you can't make measurements better than about 10% of this 2% value. And what I'm going to show you now is we can actually do something clever to improve the precision and therefore be able to detect things at very low limits of detection. Okay, so that's the basic concept. And here's the result already. I'm going to tell you how you're going to do it. But this is the previous value. Ooh, what is that? Pretty fast, huh? So anyway, this is the contrast before, and a minute or so, variation about 13%, and we're going to take it there, so really make it flat. So it's like precision sensing inside a droplet. And the answer is already here. How we're going to do it is by exploiting flow. Okay, we're going to use flow of these droplets because the flow is so regular, and we can do a lock-in with respect to both flow and microwaves. So here. Okay, so here's how this works. I'm not going to dwell too much on the details, but it's actually a very simple concept. So what we're going to do is we're going to pack each droplet with diamonds. We're going to assume that each droplet has the same amount of diamonds. Actually, it turns out to be a very good approximation. And we can move the droplets at a fixed rate. As I showed you in that movie, it's actually very possible to do so. The fastest you can move it is about 1 kilohertz, so 1,000 droplets per second. Anyway, and then what we're going to do is we're going to also apply microwaves that are modulated at a particular rate. So if you know what to look at the detector, this is what you would get from a detection. So this is a frame grab of a movie, but if you were to put it on a photodiode, this is what it would look like. This is over 500 seconds, so you'd see already that it's kind of very regular. If you zoom into a particular window, what you see is the droplet coming in and out of the field of view. So this is droplet in and out, etc. But on top of this fluorescence that you read out, you see these little wiggles. And the wiggles are the microwave modulation. So you have basically imprinted on this photoluminescence signal 2 modulations, one because of flow and one because of microwaves. And now, very easily, what you can do is do a Fourier transform of this. This is shown on a log scale, okay? So you see these very regular peaks line up on this Fourier trace. So you would imagine that you have this peak because of the droplet modulation. And because the droplet modulation is not perfectly sinusoidal, you get these harmonics at the droplet rate here. In this case, it's chosen to be about 30 hertz. And then you also have this modulation at the microwave frequency, and then you have these side bands. It's like droplet plus microwave and droplet minus microwave. And so now this gives you a very simple way to suppress noise, because you can argue that a lot of the noise comes from background that you get in your detector, or autofluorescence of the PDMS. PDMS is autofluorescent. But now if you were to do a simple normalization, so you would normalize this peak with this peak, essentially asking the only thing that you're interested in are things that are moving at the droplet frequency, so it has to be related to the droplet, as well as is modulated with the microwave. So the only thing that satisfies the intersection of both those properties is the diamond. Then you can essentially suppress every other source of noise. And this works really well. So this shrinks this distribution that we saw earlier, and we can get something like that. So this green thing is the previous distribution, but you can get something as so there. So this is the contrast value again, and to show you the extent of the stability of this measurement, this is measured over 8,000 seconds here, and you can see that this is you can have a contrast value, and you measure like 2% of this variation. So it's 2% or 5%. I'm going to not go too much in the details. I think this is showing a Fourier spectrogram in the time domain, really showing how stable this is, so that this is the droplet frequency over an hour and 104,000 droplets, and it's extremely stable. So everything is like really stable, and because of this you can make a very high precision measurement. So the common way to characterize stability is with this measurement called the Allen variance or Allen deviation. And normal experiments, because of temperature drifts or any other sort of drift, you'll get an Allen deviation that bends up after some time. So we find a very high level of stability. So even over 1,000 seconds, the Allen deviation is reducing. Basically means that you can increase improve the limit of detection by just averaging. Okay, so since I'm running slowly here, I'm just going to go a little faster. So what can you do with this? So here we have actually detected gadolinium ions inside the droplet as an example. So this is a classic paramagnetic ion that's used in the context of MRI, for example. And here you can see a very small error bar, and we find a limit of detection is about 100 nanomolar inside the droplet. This example with Tempol is another radical species. Maybe to just leave you with something, I want to put this in a context of other sensing modalities. So why is this quantum sensing? First, is this quantum sensing any better, and would it be useful? So this compares the sensing of gadolinium, because gadolinium is such a common proxy for paramagnetic ion sensing, various other techniques, EPR, fluorescence, etc., against two axes. So sample volume and analyte concentration. So ideally, you want to measure a small concentration of analyte in a small volume. So you want to be at the bottom left of this chart here. So most of the things are out there, and we are getting closer to the left bottom of this chart. The other thing that's rather interesting is the total cost of this analysis. So if you do experiments for 1 hour, which means there are something like 200,000 droplets, you can ask, what would be the cost of these diamonds that you put inside them? They look like it's really expensive. And the answer is 1 hour, so 200,000 droplets cost 63 cents of the diamond material. So it's really almost no cost. Okay, so I'm going to skip. So there are the applications we are interested in that would be, we think, impactful is to change the way flow cytometry is done by combining together now nanodiamonds with droplets and saying something useful about cells. And since I'm running short of time, I won't have time to tell you about that. But that's our a big picture angle in which we're going towards. And can I get 2 more minutes? Okay. So in 2 more minutes, so I want to leave you with saying that diamond is not the only thing, and so you don't have to be. So there are wider class of materials where this works, and so here is a big diagram chart of a material. So semiconductors are very popular: diamond, silicon carbide, HBN, silicon, etc., where you can get these spin-active centers. But that's not all. Actually, it turns out that you can get similar properties both in inorganic centers. So these are lanthanide elements, cerium, lutetium, europium, etc., but also in organic molecules. This is in the old days, of pentacene, anthracene, etc. Bell Labs was big on this in the 90s, as you might know. And so we became very interested in pentacene as an example of this. And it basically, I want to leave you just with one slide saying pentacene can do everything that diamond can do. The advantage is you don't have to, it's not diamond, so it's very cheap. You can make large crystals. You can grow them yourself. And so this is a crystal, large crystal, pretty large crystal. And the energy level diagram is the same, pretty much similar than diamond. It's just inverted. The singlet and the triplet are inverted. And I don't have much time, so I'm not going to go into the detail, but I'll just leave you with the fact that you can measure room temperature, so room temperature ODMR, very similar to diamond. And you can get very high signal to noise. I think this was slightly missed by the community. Pentacene was a very popular molecule for various things in the 90s, and then there was this resurgence of interest about centers and semiconductors, but I think there is a lot of room to play here with these materials. And so you can ask, why are these materials? I'm going to skip this slide altogether, just to say that they work exactly the same as diamond. You can measure temperature and pressure. We were able to show you can measure very high sensitivity, pressure, and temperature. But maybe I'll just leave you with this last slide saying, why would this be interesting? This would be interesting because unlike semiconductors, the spin active center now is an organic molecule. And using the power of synthetic chemistry, you can actually assemble these molecules into all kinds of interesting shapes. So we've succeeded with Jeff Reimer, my colleague, in making a porphyrin, which is a large, which is a benzene ring-like molecule, which is also spin active. And make it into a metal organic framework with large pores. So now you can imagine that you have, molecular tags that are spin active that have all these nice properties. And you can do this possibly at the single molecule level or make molecular assemblies of this type and be able to do quantum sensing just like how you would do with nanodiamonds. So let me end here because I'm out of time. I gave you some introduction of sensors. They are deployable. It's really cool because we can work in bad environments that are usually not very nice to work in. You put them into droplets, and there are actually a wide class of materials where this is possible. Let me thank the people who did the work here, all my graduate students and postdocs, funding agencies. And maybe as a last slide, I want to say that Berkeley is a good place. It's got a good view. This is the view from our lab in the sunset. This is in the winter, so it's always like this. Babukar would say that. And so if you'd like to come and visit, or we have open positions, so if this might be of interest, please contact me. Okay, thank you.
Thank you very much. We have some time for a few questions.
Can you hear me? Oh, yeah, I have a naive question. Is there any chance that you have any coupling and you get entanglement, and how would that affect the measurements you get out at the end?
Yeah, so I didn't speak anything about that. So here we're not exploiting entanglement. In other experiments we're doing using the nuclear spins inside the diamond as sensors, you can exploit entanglement. This entanglement-assisted sensing, I think, is a very exciting topic. It has a potential for giving sensitivity boosts. I would argue that it's not been demonstrated yet in a useful context, but I think there's a lot of potential for it.
So I had first, thank you for a fantastic talk and a reminder of why we like chemistry. Can you say a little bit more? You had a very small comment in there about AI applications. I wasn't quite sure what would be related there. It was a small line.
Yeah. So in these, so many applications towards these droplet sensings are in the detection of trace amount of things. So very small. I don't have the good slide here, but very small. So say it's trying to detect things at 1 molecule per 1,000 centimeter cubed or something. So if you incorporate into the droplet, most droplets have 0 molecules, and 1 droplet would have it. So the information becomes like very digital. And there's opportunities now to marry together AI-based methodologies, or because the data that's being produced here is at very high throughput. We're doing about 1,000 droplets per second, and there are applications there which we envision. This is quite widely used already. They call it digital microfluidics.
We'll take one last question just because of lunch. And so if you have any other questions, you can please come up.
Hello, I'm James Bertone, 5th year chemistry PhD student. I was wondering, on the microfluidic devices, have you all tried to incorporate them into any type of spectroscopies? Like flowing whatever, like nanocrystal droplets in water with other materials to see how that influences the spectroscopy of those materials?
Yeah, so while the pictures look very dense and you can see nanodiamonds everywhere, actually the droplet volume is pretty large and you're just diffraction limited. So there's actually quite a large space between the diamond particles. So certainly you can put other stuff inside them. And that's why we are really interested in flow cytometry. It's a kind of like, I think it's like $1 billion industry. And there's some applications we think that we can possibly get more dimensions on your flow cytometry map using these sensors. Flow cytometry is widely fluorescence-based, and possibly the applications here.
Okay, so I want to thank Ashok for making me feel really old, because my PhD thesis was on studying tennessine and paratrophenol at low temperatures doing photon echoes. So, wow, I'm real old. I guess everything comes back. That's why they call it research. Okay, so I wanted to just tell you kind of 2 quick notes. We're going to take 45 minutes for lunch. Lunch is, of course, upstairs in the physics library. And then I believe Linda wants to take another picture, but she wants to do it in front of the Widener Library, which is actually on the path to where we're going to go for dinner. And I think that's going to be maybe at 5:45. I'll try to make an announcement about that at the end of the next session. So let's thank Professor Ajoy again. And all our speakers, of course, from today. And let's have lunch.